Okay, so in this lecture, we're going to mostly focus just on working through combinatoric problems. Sometimes these problems can be tricky, not because necessarily the math is difficult, but it's kind of like the headspace you have to be in to really think about what a probability space is and how to count all the possible outcomes of a probability space and how to do that. So I think it's important to see a bunch of problems, and this is what we're going to do for the next hour and 20 minutes or so. Okay, so remember that Combinatorics has everything to do with counting. And specifically from this idea of counting, we have this handy chart that we can use to reference how it is that we decide the methodology to count. So this largely always depends on whether we're going to replace things that we've already counted. So for example, if I'm counting, if I'm pulling marbles out of a jar and I pull out a red marble, do I then place that red marble back in the jar and then do the next trial, or do I take it out and leave it? Like you could imagine the lottery, where you're trying to draw numbers, and how many more possibilities there would be if you picked a number and then replaced it, because instead of having a string of unique numbers, you would have, a string of unique numbers, you could have repeating numbers. So knowing whether you replace something that you've already chosen is extremely important, because if you do replace it, then the number of outcomes grows by quite a bit. And then the second thing to think about is if order matters. And if order matters, then you know that you're going to limit your space in some way, because you have only an order to consider and not any combination of that order. So if order doesn't matter, then we're talking about combinations. If order matters, then we're talking about permutations. Both these do not care about replacement. And if we're doing replacement, then sequences that we want to do if order matters. If order doesn't matter, then we have something that's more complicated, like the domino example from the previous lecture. So let's start by talking about and getting kind of used to n choose k, because combinations is really where both of these things kind of filter into. And particularly, how do we define n choose k? Maybe I'll do this in blue. N choose k, this is derived from the equation of P and K, and that's, actually, I'll just write this down. It'll be easier. Okay, so the equation for n choose k is going to be n factorial over n minus k factorial times k factorial. This is derived, of course, from P and k, and that gives us n minus k. So when it comes to combinations, and when we're doing combinations, we're using the binomial coefficient, which is n choose k. The big thing here that we want to remember is this hanging k off to the side here. And the reason why we have that is because we want to avoid double counting when it comes to combinations. And if you remember that we're not doing replacement, right? Because that is a tenet of combinations. Since we're not doing replacement, we don't want to double count things that we've already chosen. So this is why we have that k factorial there. So now I'll just put deal with double counting. Okay, so what is this leading up to? Well, we want to, maybe an example would be good for this. Let's consider let's consider two instances of n choose k. Let's do, well, we have about let's say in our class we have 22 students. So we have 22 students. So this is our n. And I'm going to choose, let's say that 10 students come to class all the time. So this is n choose k, so 22 choose 10. So what does this mean? Well, those 10 students who come to class, I quite like, and they work quite hard. So they're going to get extra credit because they come to class. So I'm choosing 10 students out of the 22 to receive extra credit. Now, I want to show you that is the same exact thing as saying 22 choose 12. Now, can you think about why that is the same thing? And you might want to maybe pause the video for a few seconds and just kind of think about it. Maybe I'll write this down here. 22 choose 10, and so 22 students choose 10 for extra credit. Okay, so how would we write this? We would say 22 choose 12, or I could say 22 students, and this is not like a trick or anything, but 22 students, I choose 12, I'll do this in red, not to get extra credit. So we just see that our total probability space is 22. And here I'm choosing 10, or I'm choosing 12. 10 plus 12 equals 22. So from a numerical point of view, maybe it's not as obvious, but when we attach it to this kind of real world problem, we can see that it's just these 12 students make up the rest of the probability space that was not made up in here. So 22 is our total probability space. And in this first instance, we have 10 of them. In this instance, we have 12. So it's just sort of the reflection of it, or, so to speak. So this is an important concept because that's going to be very helpful for us when we talk about combinatorial proofs coming up. So I want you to think about that. And before we do that, let's go ahead and solve 9 choose 2 plus 9 choose 3, because this is the other concept that we need to keep in mind for working on the combinatorial proofs. So, and this is mostly about the sort of steps that you can take to solve this, but it's an important concept behind it to keep in mind. So here we write this as 9 factorial over 7 factorial, 2 factorial, and that's just straight up following the equation. And this is plus 9 factorial over 6 factorial, 3 factorial. And remember that when we solve these, we don't want to do 9 factorial because that becomes a very large number, right? Because that's just 9 times 8 times 7 times blah, blah, blah times 1. That winds up being a big number, so we don't want to do that. But what we do want to do is start by saying, okay, we have a 7 factorial, that's our largest factorial on the bottom, so we can do 9 times 8 times 7 factorial over 7 factorial, 2 factorial, and the same thing over here. We have 9 times 8 times 7 factorial, 7 over 3 times 2. So we can take the 7 factorial and those can cancel out, and then our 2 factorial, which is just 2 times 1, that can cancel out, and this gives us just a 4. So 9 times 4 will give us, 36. And then over here we have 9 times 8 times 7 times 6 factorial. Forgot that. And then this actually, let me just write this. This is getting confusing. Jumping ahead. Okay, times 6 factorial over 6 factorial. 3 factorial, so we can go ahead and cancel out the 6 factorial. And then the 3 factorial is just going to be 3 times 2 times 1. So that will just give us 6. So we can just say this is plus 6, because 3 factorial is 3 times 2 times 1 over 9 times 8 times 7, and then we can there's actually a better way to do this. Let's keep the 3 factorial there, and then just do 3 times 2 times 1, and the 3 and the 9 cancel out into a 3, and the 8 and the 2 into a 4. Yeah, that looks better. So this factorial stuff gets tricky. Okay, so simple arithmetic is always the most difficult thing. So this just amounts to 3 times 4 times 7 over 1. The 1 doesn't matter. So 3 times 4, it's going to give us 12. 12 times 7 will be 84. So this will be equal to 36 plus 84, which will give us 120. So that is our final answer. Now, the numerical number of 120, interesting, but we want this to, because we're gonna use the 9 choose 2 plus the 9 choose 3 again. So I want you guys to kind of get used to those 4 numbers, particularly to get used to this idea of it equaling 120. Okay. So before we continue doing more problems, let's look at a combinatorial proof real quick, because it's a good way to kind of get in the mindset of thinking about how probability spaces work. So we showed just now, we'll keep doing it in purple, that previously on last week's episode, we had 9 choose 2 plus 9 choose 3. And we said that was equal to 120. We calculated that. And I want to do this in yellow. Let's see. I'll just write. So look at 10, choose 3. And I guess we'll just solve real quick. This will be 10 times 9 times 8, 10 times 9 times 8, and times 7 factorial, but the 7 factorial will just cancel out from the bottom. And so we're left with 3 times 2, of course, times 1. And then this will become a 3, and this will become a 4. You can just follow the same steps from the last slide, but this will also equal, this is the important thing, 120. So 120 and 120. Now, why is that interesting? Well, if we think about like equality and what it means to be equal, we can say that like it's not a stretch to say that, okay, this in green, like 120 equals 120, right? So we could say then that 9 choose 2 plus 9 choose 3 is equal to 10 choose 3. Now, I mean, when we're talking about proofs, we don't want to use just examples like this. We want to use, other things like, reality. We would want to use like n choose k, and then things like n and k plus 1, and then n plus 1 and k plus 1. We want to use those kind of things instead of the step that we have here. But that's just a generalization, and it makes it a little bit easier to kind of look and think through this when using real numbers. So we'll keep working at that angle in this example. But how can we really think about a way to prove that these two things are equivalent beyond just solving them? And the reason why is if you can think about a way to argue this proof without just the numerical solution that says that they're equivalent, if you can think about it in terms of a probability space, then it can really help to illuminate the ideas that you're going to have to wrap your head around to think about like problems in terms of probability spaces. And a really great way to do this is with coin flips. So I'll go ahead and if you want, you can pause the video for a few minutes and kind of think about how you might prove this using coin flips. And maybe as a quick aside, we can kind of think about coin flips. And let's say that we have 10 flips, and we want to see, how many, how many ways can we get 3 heads and 7 tails, and we assume it's a fair coin. Not that that really matters, but it's an assumption. And we wanted to see how many ways we can get 3 heads and 7 tails and 10 flips of the coin. So that's the key thing, 10 flips. So this is like saying 10 choose 3. Now, one important like facet of this problem to think about is, and let's just like enumerate an instance of these. That's our 3 heads, and then here's our 4, 7 tails. So remember that this head right here is unique, and this tail is unique. And in fact, all 7 of these tails and all 3 of these heads are unique. And if you get this head once, that's the one time you've gotten that head, and you cannot ever get that head again. So these are essentially the number of permutations. These are the number of permutations. And it's really, if we can take the 10 choose 3, we can see maybe in an equation form, might make a little more sense. So 10 over 3 factorial, 7 factorial. So what does this mean? Like specifically the 7 and 10 and the 3. So kind of 10 factorial is the total amount that we can sort of get, and the 3, let's put like, that can be thought of as the total, and 3 is the number of ways to rearrange the heads, and this is the same way for the tails. So 3 factorial of the what we use as the example is the number of ways in which we can rearrange these 3 heads, because each of these heads is unique, and once we used it once, we can't use it again in that same spot. So once we have this head here, it must stay, and these 2 can swap places. And then once this one's here, it's to stay, and then these 2 can swap places, so on and so forth. So that's such that we have these 3 heads, and how many different orientations can we have of them. Same thing for the tails, and then of course we have the total space. So the and I guess another important consideration to think about before I go on, and maybe this is 2 things to think about. One is we just can't use 10 factorial for a total probability space because there's a lot of double counting in here. Like if we were to keep this head here fixed and then shuffle all of these, there are a lot of instances that we can create where we're duplicating this h. So those are just something to keep in mind, that the reason why it's not just 10 factorial is because there's a lot of duplications here. The second thing to think about is, maybe it's like a grander idea. Why we want to show that these kind of things are equal, like a way to think about it is, let's say that you have all the components to build a car. There's thousands of components to build a car. There are a lot of different ways that you could build it, and there's a lot of different orders that you could use to build a car. And so at the end of the day, you still get the same car, but there's just different orders in which you could configure certain parts. And so we want to just show that regardless of how you decide to go about configuring and building the car from the component parts, at the end of the day, you still get the same car. So that's helpful or not, that's just one way to kind of think about, to wrap your mind around like what we're trying to show here. Okay, so we have set this problem with heads and tails and with 10 flips, and we want to so let's go into kind of a little more proof mode here. So we have our claim, and well, I'll write this up here. Okay, so we want proof that 9 choose That was ugly. 9 choose 2 plus 9 choose 3 is equal to 10 choose 3. And our claim is that both sides, so that's the 9 choose 2 plus 9 choose 3, and the other side, 10 choose 3. So both sides count the number of ways to get 3 heads from 10 flips, right? 10 choose 3, 10 flips choose 3 heads is the same thing as saying 9 choose 2 plus 9 choose 3, 9 choose 2, 9 choose 3, yeah. So, and that's what we're trying to show. So, coin flips have a nice natural property that whenever you do a trial of a coin flip, you have a 50-50 chance of having either heads or tails. And so how can we use that benefit to us to show 9 choose 2 and to show 9 choose 3? So let's consider we have two diverging paths. And the first path, the first path is if we get a heads, and the second path would be if we get a tails. So maybe we can write down these two cases. So and ultimately this is going to lead us down the path of 9 choose 2 and 9 choose 3. Maybe I'll write that. So for 9 choose 2, we have a trial where we've gotten a heads, and then that's our first one, and then okay. So this is obviously our first flip is heads. So and then for our second one, we'll have our this will be our second experiment, but our first flip in this case is tails. Okay, so this is going to equal tails as our first one. And okay, so the key idea here is that when we first start out this trial, we flip a coin, and there's only two paths we can take, and that is the path where we get a heads first or we get a tails first. If we get a heads first, this is saying essentially now we have a condition where it's going to be 9 choose 2, because we know our first coin flip is a heads. So going forward, then we're going to fill in to these last 9 spots is going to be some amount of 2 heads and 7 tails. Capital. 7 tails. And the same is true for this one, where we have tails, so we're going to have 3 heads and 6 tails, which is why this is 9 choose 2, because now in this space I have 9 choosing 2 heads, and in this one I have 9 choosing 3 heads. And we want to show that those are both equal to the case where we have 10 choose 3, 10 coin flips choose 3 heads. So the key idea to keep in mind is that you have both 9 choose 2 plus 9 choose 3 and 10 choose 3 are counting the same exact thing. And this goes back to that very first example right here, this logical leap. So let's maybe write this out because it will be, so let's do it in green. So 9 choose 2 plus 9 choose 3 is the same thing as 10 choose 3. And why? Because 10 choose 3 is 10 flips choosing 3 heads. And both of these things together, 9 choose 2 plus 9 choose 3, is like saying, give me all the cases where we have 2 heads and we're going to have 7 tails, and this is the remainder of the probability space, 3 heads and 6 tails. So they're essentially counting the same things. This is the entire probability space of 10 coin flips packaged into one n choose k. And this is the entire probability space as well. It's just packaged into the other 2 halves. So maybe like pictorially, maybe this would be better actually to use different colors. So we'll use green for 10 choose 3. So we'll say these are a 10. So this is the entire probability space. And it'll probably be something that's a little bit like that. Like that. So the way to kind of think about the same thing is that they both describe the same outcome. It's just one of them has the entire outcome packaged in one 10 choose 3, whereas this one is packaged into just 2 separate kind of experimental outcomes. The experiment being the coin flips. 9 choose 2 and then 9 choose 3. And when you combine both of those, you get the probability space that 10 choose 3 is primarily discussing or is interested in. And so that's why we're saying that these things must be equal, because even though they describe, or they might look different, they describe the same overall outcomes. And that in itself is a combinatorial proof, is to show that equivalence of outcomes. And like I said in the slide before, yes, we're using 9 and 2, 9 and 3, and 10 and 3, but this also generalizes to nk and n plus 1, n plus 1, k plus 1. So, these things, will generalize. So I think this is kind of like mathematically it's not hard, but it's the wrapping your head around it is kind of difficult to think about. But combinatorial proofs are quite difficult for that reason, but they offer a lot of interesting insight, and it's worth kind of exploring it a little bit. And who knows, there might be a combinatorial proof on the final exam. But if I do decide to put it on the final exam, I will let you know so that you can spend some extra time thinking about this concept, because it's not easy. This really leads us is that we want to use combinatorics as a tool for probability. And the reason why is this idea of a sample space. The sample space is like one of the most key ideas to keep in mind when we're thinking about probability. Because if you can define your sample space, then you can really begin to understand how to define the outcomes from that the outcomes from that probability space. So here we have, I won't labor this on too much, but S, which is our sample space, is equal to set of all possible outcomes. I use that word in all caps because it really is about all the outcomes, and that's all the positive outcomes. That not to say, the outcome of everything that's going to happen in this world, but for the thing that you're interested in, the outcomes for that. For example, like 10 choose 3, the possible outcome, all of the outcomes of how to choose 3 heads from 10 coin flips is your probability space. And if you can define your probability space, then it can make solving these kind of problems much easier, because you're just trying to figure out how to count. Given your S, your S, you're just trying to figure out how to count all the possible A's that can come from that, the outcomes. And A is an event, for example, flipping coins. So always think about your probability spaces, because unless you know your probability space, it's really hard to think about a way of counting events and outcomes of those events from your probability space. Okay, so let's continue on with solving more problems. So this problem is asking us to consider our last question. We were selecting Avi from the list from our class of 20 students, and now we're doing it with replacement. And we want to know intuitively, is that going to result in there being equal, greater, or less than the same probability that we had before, which was 1/4 or 25%. So we could say without replacement, the probability of selecting Avi was equal to 25%. So now that we have with replacement, the probability of selecting Avi, what is that going to be? Well, we can really think about this question, instead of, since we have, I guess a good way to think about it is since we have replacement, the question now becomes the probability of selecting Avi at least once, because we haven't, it's not specified whether it's selecting Avi twice or 5 times. So we can just assume that given 5 chances of selecting a student, one of them needs to be Avi with replacement. So maybe we'll get a little bit more specific. I'll switch. The probability of selecting Avi at least once. And we should really draw heavily on here with the complement rule. So we could say it's 1 minus the probability that Avi is never selected. And for that, that's just a much simpler question to answer, and that allows us to make use of this rule way back here. With replacement. So for that, we're just going to say it's 1 minus, and the probability that Avi is never selected for any given trial is 19 over 20, because we have 19 students who aren't Avi and 20 total students, and that's to the 5th power because we're going to do it 5 times. And what that winds up being is, let's get my calculator. Okay, about 22%. So the answer here would be less than. And intuitively, why that makes sense is that because we have, without replacement, we can think about it. Let's draw these 5 trials, 2, 3, 4, 5. Okay, so without replacement, so we pick a student, and then we pick another student. The first time we pick a student, we have a 1 in 20 chance of it being Avi. The second time, if we don't pick Avi, we have a 1 in 19, and then a 1 in 18, and then a 1 in 17, and then a 1 in 16. So, sorry if you hear some of the dogs going nuts in the neighborhood. There was an ambulance that just went by a block away. Okay. So the probability of the chance of Avi getting picked kind of goes up as we do more selections from students because there's no replacement. So that probability is going to be higher that Avi gets selected without replacement because we've got 5 chances to pick him, and every time we don't pick him, there's less people to pick from. So that's kind of why this is the first event, second, and then this would be the 5th event. When we have replacement, so I guess this is without replacement, and then when we have with replacement, every single trial, let's draw the same picture, 1, 2, 3, 4, 5. Every single one of them is 1/20th. Oh, we didn't pick Avi, put that student back in. Okay, now we have 1/20th again. Didn't pick Avi, okay, put that student back in. 1/20th, we didn't pick Avi. Okay, put that student back in. And so you can see like every single one of these trials is always a 1 in 20 chance that Avi is picked, because we're always replacing the student that we picked and putting them back into the pool. Also, this is the fact that we can have duplicates too. So we could have, let's say like student 19 is Jason and student 20 is Avi. We could select, Jason, 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 and Jason, and never see Avi. And that would be that, we can get just 5 of the same student. So that's why the probability is lower intuitively when you have with replacement. You're kind of like resetting the game every time you play. So the original odds are still there. Okay, let's do our last one. This will be the unfair coin example, and then in class we'll do a bunch more of these examples during the hands-on problem solving and stuff. We'll step through even more examples. This video is already getting long enough, but I really want to step through these things slowly and kind of explain everything. On the website, if you haven't seen it yet, there's a video of, I think it's 2 YouTube videos that Suraj has created when he taught the class. Yeah, those are pretty good. Next, we'll be doing the unfair coin example. On the class website, there was a video that Suraj, who previously taught this class, created. And in those 2 YouTube videos, which is a link to that playlist, he goes through more examples of combinatorics. But he did one example, I believe, of a unfair coin. And we want to do some more examples on unfair coins because it kind of changes how we think about things a little bit. So one thing with so if you haven't seen that video yet, go watch it, and then you can come back and finish these. Probably the best way to do it. But in this example, we have an unfair coin. This is really the key here, is that bias, such that for each flip, the probability of heads is 1/3, which, if we know, remember about the complement rule, that would imply that the probability of tails is 2/3. And then we can also assume, so each trial or each flip is an independent event. Okay, so that's what we'll assume. So what is the probability that we see the specific sequence head, 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 tails, 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 tails? So this is 4 and 6, so 4 heads, 6 tails. Now, each of these events, so the probability of seeing, it's in blue, 4 heads and 6 tails, is equal to, this is a very straight answer, the probability of heads, which is 1/3. Because remember, all of these events in the sequence are independent. So we have a 1/3 chance of getting a head, and then we have another 1/3 chance of getting a head, so on and so forth. And then we also have a 2/3 and a 2/3, and I bet you can guess that I'll be writing this 3 more times. Okay. Now the question is, these are all independent events, so what do we put in between these things? Well, these are independent, so we're just going to go ahead and multiply all these together. So we're just taking the straight probability of any individual event occurring and then stringing them all together. And we can further reduce this by saying it is equal to 1/3 to the 4th times 2/3 to the 6th. And I'll let you do that calculation. Or like on an exam, you could just leave that, and that would be our our final answer, and that would be completely fine. Okay. So what about the probability that we see exactly 4 heads? So what does the probability space of that look like? And remember, we've got 10 coin flips. So we got 2 things to consider. One, we've got 10 coin flips, and then we also have a bias in here that we have to think about. So what's the probability space? Well, I like to think of this as equal to some really large thing where we're going to have let's do all purple. That's fine. Heads, 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 and then tails, 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 tails. And then we're also going to have heads, 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 tails, heads, tails, 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 tails. Then heads, heads, tails, tails, heads, tails, 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 tails. Okay, so on and so forth until we get to something that would be like tails, 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 heads. Right, so this just describes the entire range of sequences that we could have, because each of these is a sequence. So a sequence of 4 heads and 6 tails. And we have, a certain number of them. So we're trying to find out what is the probability that we see exactly 4 heads. So all these sequences here are, well, I suppose this is really describing, that is incorrect. So this is describing sort of like the all the possible events that we care about, because in all these sequences of 10 coin flips, we have 4 heads. Doesn't matter what order we see them in, they're just sequences where we see 4 heads. The total probability space, so S would equal all sequences of 10 flips, including all heads and all tails. So that's all of them. We only care about the events where there's at least 4 heads. So the question we're trying to ask is the number of ways to arrange 4 heads and 6 tails. So the question we want to ask is the number of ways to arrange 4 heads and 6 tails. And that winds up being 10, choose 4, because we care about the 4 heads. And so we can write this as a probability of getting 4 heads, 6 tails. That equals the number of ways of seeing 4 heads and 6 tails. So that kind of is this information right here. And that's going to be, I'll just put this right there, multiplied by the probability of one such sequence because anytime we have an event where we flip 10 coins, what's the probability of seeing one sequence that at least has 4 heads? And we want that multiplied by the total number of ways that we can arrange or see 4 heads and 6 tails. So this winds up being, this in yellow, are 10, choose 4. So this is the number of ways to arrange or number of sequences that we can see 4 heads and 6 tails. So this is kind of like, would be equivalent to our A times 1/3 to the 4th times 2/3 to the 6th, because that is the probability of seeing one such sequence, which is the answer that we got from the first question. So that comes from this. All right, so we have 2 things that make this. Maybe I'll just put the probability of seeing one such sequence, which is this, and then the number of ways to arrange 4 heads and 6 tails, which is all of this over here. So that's kind of where it all comes together. And I suppose you could also say that this is this, and hopefully all this color is not too confusing. I just want to show you where all the parts and pieces kind of come from. All right, yeah, it's sloppy. Might not be any better. Okay. All right. Last 2 problems. What is the probability that we see exactly k heads where k is greater than or equal to 0 and less than or equal to 10? So this is the number of ways to arrange or see k heads and 10 minus k tails, right? Because it can either be k can either be 0, in which case you'd have 10 tails, or k can be 10, in which case you'd have 0 tails. So this winds up not being a tremendously, it's worded or it looks kind of maybe scary, but if we think about it, it's not too bad. So we have k heads and 10 minus k tails. That's the probability that we're looking for, right? To see exactly k heads, where k can be any number between 0 and 10. Therefore, k varies, but tails is always 10 minus k, because it's two outcomes from an event, and those outcomes are 1/3 heads and 2/3 tails. So we can just follow the same equation that we had last time from the last question and say that this is equal to 10 choose k, because we have k heads, and that's going to be multiplied by 1/3, because that's the probability of getting a head, and that's k heads, multiplied, right? We had 4 up there, usually 1/3 of the 4th, because that was the probability. Before we were concerned about getting 4 heads. Now we're concerned about getting k heads, and this is going to be just 2/3 to the 10 minus k. And what this is saying, specifically this is the number of ways to arrange k heads and 10 minus k tails. And this winds up being our final answer for this problem. Okay, next one. What is the probability that we see at least k heads where 0 is less than or equal to k, which is less than or equal to 10? So what's the difference here? This problem looks exactly the same, which is why it's important that we read it. This is covering it up a little bit, so let me fix that. Okay, I will highlight the key thing here. Before we were concerned about seeing exactly k heads. Now we're interested in at least k heads. So let's write out what the probability statement for that is. So this will be the probability of at least k heads, which is going to equal the probability of getting k heads, because we need that, plus the probability of getting k plus 1 heads, plus the probability of getting at least 10 heads. Because we have at least, we have to get every instance of k heads here, so it's a summation essentially. So where does this lead us to? This leads us to the sum to k from the sum of the 10 that we have from the starting point, which is I equals k. And here we have 10, choose I, because I is equal to k. So we're going to be essentially we're doing is we're summing up. I want to make this clear maybe. What this is saying here, what we're trying to describe, is a summation of probability events, and these are different probabilities because every time we do a trial for k, we have a different probability, which is why we have to sum them all up. So here we have 10 choose I, because we've got 10 possibilities. We're choosing I heads, and I is dependent upon being greater than or equal to 0 and less than or equal to 10. So that's the confusing part there. Then the rest of it is just like the first question that we answered, where we're going to be using this. And that is just our bias. So this would normally be 1/2 if it was an unbiased coin, and this would be 1/2 as well if it was an unbiased coin, because this is the as we said here, the probability of getting heads was 1/3. So this is our biased heads, and this is our biased tails. Okay, so now back to the same of the equation. So we have 1/3 to what power? And if we think what's going on here, 10 choose k, the probability of getting heads to the kth power, times the probability of getting tails to the 10 minus k power. So we just simply fill it in. This is now I, and this is 10 minus I. We use I here instead of k because we're writing this expression in the form of a summation. And in the form of a summation, we have this summation variable here that, or nomenclature, where we have I iterations, and we're saying that equal to whatever k is. And so then we just fill in I where the k would have been to keep this in the summation nomenclature. And that's that's it for this problem. We're able to write this in the form of a summation, and it describes the probability that we see at least k heads for any instance of k ranging from the value of 0 to 10. So this one is probably a little bit less intuitive, especially these last two. I mean, it's not the mechanics that are going to mess you up. It's going to be the thinking logically through the problem and having that intuition. So I would say on probability problems like this, they typically start off, much simpler, and the things you learn from these much simpler examples, for example, the probability of getting a specific sequence and the probability of getting at least that sequence in any combination or in any order. Like these things are built up because they're giving us parts and pieces that we can use to answer these more difficult questions. Okay. So that's all for this lecture, which has gone on probably a little bit longer than it should, but these are just problems. So if you already know how to do this stuff, you probably aren't watching right now. But if you don't know how to do it, then maybe you're happy that there's some more problems to look at. In class, we'll go over some more problems, of course, and we'll have more problems in the discussion section and the homework as well. There will be a couple of these longer problems. All right, well, that's it for this lecture, and we'll move on to the next lecture, which will be talking more about things like Bayesian probability and total probability, which we'll need for our more advanced probability stuff that we're going to be doing as we connect probability back to machine learning and data science. All right.